And Petroleum Engineering Department. The title of the presentation will be Promoted Platinum Catalyst for the Dry Reforming of Methane in the Presence of Oxygen. And presenting this morning will be Dr. Susan Stagg-Williams. And
thank you. First of all, I'd like to say thank you to Dr. Davis for inviting me to speak at this symposium, honoring him. It's a great honor for me to be able to give this presentation and to be in the company of such respected researchers and previous award winners. This is going to be somewhat of a shift from the talks that we've been just listening to. In our research group, we don't work with coal, but we work with methane and trying to get to synthesis gas for future isotope processing. So it's a kind of a little bit of a shift. And with that, I thought I'd go into some background into the production of synthesis gas. Yesterday, Enrique Iglesias gave a very nice talk on the conversion of methane and some of the routes for that conversion. He talked about the fact that there are direct routes and indirect routes. And the pathways that we are considering are those that are considered to be the indirect routes to synthesis gas. On the left-hand side here, we have some of the reactions that are being investigated with the various ratios of hydrogen to CO that they produce. And then on the right-hand side, the variety of products that can be made from synthesis gas. What you can see is that the primary products require a 2-to-1 ratio of synthesis gas and isotope processing. There are some 1-to-1 product ratios that are required for the production of polyethylenes. And what we have been searching for, what we have been looking for, are components or catalysts that can basically operate in a variety of conditions. So for steam reforming, for dry reforming, for partial oxidation. We're not looking for materials that are the best in each category, but material that would be able to operate fairly well in each range, such that we can come up with a tunable system. Simply by changing your feed conditions, the amount of steam, the amount of CO2, the amount of oxygen, you would be able to arrive at a variety of hydrogen to CO ratios for whatever processing might be required. Just to highlight some of the reactions, the primary reactions that we've been interested in, steam reforming is obviously very well known and very much used because of its inexpensive feedstock. However, you get high product ratio and very endothermic. These are kind of the classic slides that you would see for production of synthesis gas. Partial oxidation is being studied very much now in terms of using oxygen permeable membranes. This reaction gives you your 2-to-1 product ratio that is desired, and it's exothermic. Problems with that can be design and control of the reactors as well as the cost of oxygen. And it's been shown that unless you have a very large plant, getting the oxygen becomes your limiting factor and making the processing not feasible. A lot of the work that's being done in oxygen permeable membranes is somewhat limited by the flux of oxygen through those membranes. And we'll talk about later how we're trying to shift our work into using those membranes, combining dry reforming and steam reforming. On the right-hand side is dry reforming reaction, which has the advantages of your inexpensive feedstock with simultaneous availability, your lower 1-to-1 product ratio, which allows you to do mixed reforming reactions. The problems with that are catalyst deactivation due to carbon deposition, and the fact that the reaction is again very endothermic. As kind of a side note, one of the things that I think has been kind of missed in the literature, or missed in terms of studying, are the endothermicity and the heat effects that take place with this reaction. And it's my opinion that with dry reforming and in talking with colleagues, that really is going to be a limiting factor, or would be a limiting factor in terms of becoming an industrial viable reaction. Some of the previous work that's been done on the role of the support for the dry reforming reaction, Johannes Fletcher and Julian Ross and Bradford and Van Nuys looked at a variety of supports, and acidic supports have been found into carbon formation. Supports with low surface area at high temperatures lead to low activity. And although silica may be a viable support if you're operating at lower temperature, you're limited by your equilibrium conversions at those temperatures. When you start going up to 800, 850, 900 degrees, supports with high oxygen exchange capacity, and we used Syria and zirconia promoted catalyst supports with platinum on those materials, and showed that you could see increased stability and increased activity with the promotion of Syria with zirconia. That promotion came from the fact that the oxygen exchange aided in the removal of carbon or the cleaning of metal, and I'll talk about that further. We also saw that supports that form carbonates were able to perform well for the reaction, particularly lanthanum-promoted zirconium materials, and this was in agreement with other reports that had been previously shown in the literature. One of the things that we found on the lanthanum zirconium materials was that it was not only the formation of carbonates that was important, but the fact that those carbonates would then be more active or more reactive than carbonates formed, say, on the zirconium by themselves. This is a cartoon picture of the reaction schematic for what's happening with methane and CO2 reforming on a reducible support. Right, that's a key point. The first step is that you have methane decomposition occurring on the platinum particle, and here's the cartoon of your reducible oxide. When that methane comes down on the platinum particle and decomposes, the carbon that's on the metal can interact with oxygen from the support, forming carbon monoxide and hydrogen in the gas phase. When you have CO2 absorption on the support and dissociation, that occurs at the site of the oxygen vacancy. So CO2 absorbs at that site. The CO2 dissociates and oxygen replenishes the vacancy in the support. And when those two happen together, you have this concerted mechanism, right, where you have decomposition and dissociation occurring simultaneously. What we found is that it was the balance between the rates of that decomposition and the dissociation which determined the long-term activity and stability of the material. Right, so materials that were able to do this step, the decomposition well as the dissociation, and be reducible were the ones that showed the best activity. How we came up with this mechanism, or how we verified this mechanism on the different supports that we had studied, was the first thing we looked at carbon-13 labeled pulses of methane. We did some isotopic studies, and what we found is that when you take platinum zirconia and you pulse carbon-13 labeled methane at 800 degrees, you see the formation of hydrogen, but you also see the formation of a significant amount of carbon-13 labeled CO. Zirconia is the only source of oxygen in the system, and therefore that oxygen must be coming from the support. We then followed up those pulses by carbon-12 labeled CO on the same material, and what you can see is that there's the appearance of not only carbon-12 CO, which would come from dissociation, but there's also the appearance of carbon-13 CO, which would come from removal of the carbon on the metal by the oxygen formed during the dissociation. What we also noticed was that after a series of pulses, or after a number of pulses, the CO2 dissociation stopped, and we no longer saw dissociation of the metal. We thought that there might be oxidation or partial oxidation of the platinum metal. We've done some studies where we had then pulsed methane afterwards, and we do not see the formation of water, which would indicate that there is no surface oxidation of this material. We've also looked at these materials under X-AFS, and we don't see any oxidation either. So we wanted to now probe why that CO2 dissociation was stopping, what was happening with that mechanism for that to occur. We did some drift studies on pre-oxidized and pre-reduced platinum zirconium material. We oxidized these materials at 300 degrees C and then did a low temperature reduction so that we would only reduce the metal and not reduce any of the support material. After that pre-oxidation pre-reduction, we exposed it to carbon dioxide at 300, and we saw no CO band on the metal, so no linearly absorbed CO. We cooled this material down to room temperature, and then we exposed to C2H4 to try and impose some surface contaminants or some hydrocarbon species on the surface. We then heated that material up in argon, and when we heated that material up, we now see the appearance of the linearly absorbed CO at 2070 on the metal. What's happening here is that the hydrocarbon is decomposing. When the hydrocarbon decomposes, it reduces the zirconium support, forms CO, and that CO shows up as linearly absorbed CO on the metal. If we continue to heat an argon to 300 degrees C, the CO band disappears. So now what we've done is, if you envision the surface, we have a reduced metal, we have a reduced support material around it, and we have no CO on the metal. If we now expose it to carbon dioxide at 300 tried to investigate this mechanism with the addition of the promoters. So if we added the lanthanum to the zirconia, did we see a change in the necessity for the oxygen vacancies? What we've done is here we have a 1.5 weight percent platinum on lanthanum zirconia with 5 weight percent lanthanum. We exposed it to pulses of CO2, followed by pulses of methane, followed by pulses of CO2. And, excuse me, this is the production of CO during those pulses. What you can see is during the first case where we have reduced it at low temperatures and heated up to 800, we don't see any CO2 or CO formation during those first set of CO2 pulses. So we are not seeing CO2 dissociation. When we have the methane pulses following, we now see the production of CO, again showing some reduction and possibly some dissociation of carbonates that may have been formed on the surface. Now when we do subsequent pulses of CO2, we see the formation of CO, indicating that the oxygen vacancies are necessary for that dissociation of CO2 to occur. One study that was interesting on this is that when we did pulses of methane after putting CO2 on the surface. So in this case, we have CO2 on the surface here. We've now done pulses of CO, as opposed to cases where we do pulses of methane first with no CO2 on the surface. We see more CO being formed when CO2 is present on the surface first, right? And so what we're thinking in that case is that when you put CO2 on the surface, lanthanum has the ability to form carbonates of benzene due to the basicity. When you put the methane in there, you now have a more reactive or an active carbonate species that can react with the carbon from the methane to form additional CO. A really nice study that was recently done by Rosasco and co-workers while I was on sabbatical was to look at the evidence for the dual path mechanism on Syria. And what has been done in this study is they've taken Syria overlayers on platinum 111 and done different pre-treatments and different reaction conditions, and then used XPS to measure the fraction or the amount of reduced and oxidized or Syria 4 plus and Syria 3 plus on the surface. In this case here, the pre-treatment in the first condition is just oxidation at 760 degrees C, and you see that 100% are all of the series in the 4 plus state. If you do the reaction of methane and CO2 at a 1-to-1 ratio, you now see that you have about 80% of the Syria in the 4 plus state. Right? That would come from the fact that when you have the dry reforming reaction, you have the balance between these two paths. This is what I talked about before. Reduction with methane would take it from Syria 4 plus to Syria 3 plus, and oxidation with CO2 would take it from the 3 plus to the 4 plus state. Right? If you then take the same material and reduce it in CO so that you're now inducing more vacancies or reducing the support more, you see that your fraction of Syria 3 plus or Syria 4 plus decreases to roughly 60-62%. Following that, if you then do reaction again, and you see that your amount of Syria 4 plus goes back to the same state that was originally at when you first did the reaction. Right? Showing that in this case, during the reaction, you have the balance between those two mechanisms, and that you should end up with the same level of Syria reduction, which that level determines your long-term stability of your material. To go into some of the work that we've been doing recently, we were, again, like I said, trying to investigate materials that would be able to operate under different conditions, so in the presence of oxygen and in the presence of water. We also wanted to investigate alternate catalysts for the CO2 reforming reaction, so to try and enhance that oxygen transfer mechanism and look at high oxygen transfer materials, such as perovskites, strontium, iron, cobalt. This material has been used a lot in the past several years for the production of oxygen permeable membranes. These membranes have been shown to be more stable at high temperatures as opposed to perovskite membranes. And so we thought we would try this as a support material first, just with platinum on top of that. And then also try a dual promoter we tried to promote the metal, where we tried to actually add tin, which would be a common reforming material, to try and prevent carbon deposition from occurring on the platinum metal. What we found is that when we added tin, that didn't work because of the fact that during the reaction you had segregation of the platinum and tin. The tin formed islands around the platinum, or rings around the platinum metal, that blocked your interaction between the metal and the support and decreased our overall activity. Some of the work that we have been looking at has been based on recent studies by Richardson at Houston, where they've shown that the addition of rhenium can result in improved performance for these reactions. And we're currently doing some studies with platinum on rhenium to figure out if those improved activities hold true in the presence of the ceria and the lanthanum, where that interaction between the metal and the support is of utmost importance. The catalyst preparation, all of the zirconia catalysts that we have were obtained from MEI chemicals. We prepared the lanthanum cobalt oxide using the citric acid method, and strontium iron cobalt oxide we obtained for superconductive components. We also have prepared a strontium iron cobalt oxide material ourselves in the lab, and we didn't see any difference between the activity in a citric acid preparation that we did and the one that came for superconductive components. On the ceria zirconia catalyst, we used the 18 weight % ceria zirconia. The lanthanum zirconia had 5 weight % lanthanum, and two catalysts had the same weight % of both of them to try and look at the effect it had by dual component catalysts. All materials for calcine are all supported for calcine at 800 degrees C for 4 hours before the addition of the metal. We use loadings of platinum primarily of 0.5 weight %, and then we also have 1.5 weight % platinum zirconia catalyst for comparison. And then we calcined all materials at 400 after the addition of the metal. For our activity studies, all of the catalysts were reduced at 500 degrees prior to reaction. When we did methane and CO2, we had a 1-to-1 ratio of methane and CO2 at 800 degrees at high gas balance phase velocities. Previous studies that we had done had all been at the ratio of 2-to-1 methane to CO2 under highly deactivated conditions, and we wanted to do these studies under conditions that would be more reasonable for industrial applications. When we have methane, CO2, and oxygen present, we looked at several different ratios. This first ratio here is along the lines of what you would see for more of a true autothermal reforming conditions in terms of a higher ratio of oxygen to CO2. The last two that we looked at were primarily for our own interest because of the fact that we are trying to look at using oxygen permeable membranes, and rather than using those membranes where oxygen is a primary component, like for partial oxidation reactions, we're interested in looking at these dense oxygen permeable membranes to bring or bleed oxygen in as a supplement for a reaction in which carbon deposition occurs. What we're interested in doing then is to see what happens if we have a dry reforming ratio, a 1-to-1 ratio, or close to a 1-to-1 ratio with then some oxygen being added in. And these are the first two ratios of the study that we've been doing. Excuse me. Temperature programmed reduction studies that we've done have all been in 5% hydrogen and argon, and TPOs after reaction in 5% oxygen and helium. When we did the characterization of the lanthanum cobalt oxide and the strontium iron cobalt oxide before reaction, we see with the BETs we had very low surface areas after calcination at 800 degrees. Hydrogen chem absorption was done after reduction and then heating up to 800, followed by low temperature reduction again. And so you can see that our platinum dispersion is very, very low on these materials. X-ray diffraction before reaction, so we had the perovskite structure and we had the crystalline structure associated with this material. Activity studies showed poor performance for the perovskite material and no performance or no activity for the strontium iron cobalt oxide. You see an induction period here for the perovskite material followed by a decline in activity, and that induction period could be due to some encapsulation of the metal during the high temperature treatment and reduction. And this has been compared here to the platinum zirconia catalyst that we'll see later. When we did temperature programmed oxidation after reaction on the perovskite material, we saw 2 small CO2 peaks at lower temperatures and a very large CO2 peak formed at higher temperatures. So this deactivation is most likely due to carbon deposition of the material. Temperature programmed reduction experiments on the perovskite and the strontium iron cobalt show that you have reduction of either the formation of La2O3 of this material, or it could be due to cobalt oxide species that are being produced. And it's been shown that if you use the citric acid method with nitrate materials in the preparation, that you can have this material on the surface, which would then be produced, forming a peak around 500 to 600 degrees. So this peak could have be due to the presence of both of those reductions occurring. With the strontium iron cobalt, we see two reduction peaks after the reduction of the metal, and those are most likely due to the reduction of the support material. When we've done X-ray diffraction on these materials after reaction, for the strontium iron cobalt, we see no diffraction peaks observed at all. So it's a completely amorphous material. Reduction at 300 degrees, we did low temperature reduction to try and avoid that reduction of the metal that we saw happening between, or the reduction of the support happening between 400 and 500 degrees. So we did a low temperature reduction followed by reaction, and we still saw no activity. We also took this material up to 800 degrees, did pulsatile oxygen to try and see if possibly the metal had been covered by the support prior to doing reaction, and we saw no increase in activity. For the perovskite material, after reaction, the X-ray diffraction shows the loss of the perovskite structure. We see minor peaks indicating a conversion to La2O3, but we see no peaks observed for platinum, carbon, or any of the cobalt material that may be present on the surface. When we looked at the perovskite now in the presence of oxygen, and we pretty much abandoned the strontium iron cobalt, so you won't see that appearing anywhere else. When we've done the presence of oxygen on the perovskite material, we see a dramatic increase in the initial activity, and that most likely is due to oxygen that is aiding in the uncovering of the platinum, as well as just oxygen converting to methane due to, with a high amount of oxygen, having a reaction to CO2 and water. We see a rapid decrease in the activity, rapid deactivation, again due to carbon formation on the material. We now focused our efforts on looking at the promoted zirconia catalyst, and this is a pre-characterization for those materials. BET surface area before reaction or after calcination at 800 for the supports show that the lanthanum zirconia has the highest surface area. The platinum series zirconia and the lanthanum series zirconia surface areas are very similar, and all three are higher than BET. And just as a side note, for those of you who may have a copy of the preprint, there's a typo in this value. Although I would love to be able to say we reduced zeolitic surface areas, this number is 46, not 246. So if you have the preprint, please make a note of that. Hydrogen chemisorptions, again after heating to 800, we see that the dispersion on the platinum zirconia catalyst is high. The 1.5 weight percent catalyst has a lower dispersion, followed from the series zirconia. The lanthanum zirconia was the one that was the lowest. And these are in good agreement with results that we had previously done on the 1.5 weight percent platinum on those three materials, which showed that if you have lanthanum zirconia before reaction, that material has the highest amount of, or the lowest particle size, or the lowest dispersion, I'm sorry, followed by the series zirconia and then by the zirconia. If you then run these after reaction with the 1.5 weight percent material, we see that the addition of the promoter helps to aid reduction of sintering of the metal. So these dispersions change during the reaction conditions. X-ray diffraction showed monoclinic forms of the zirconia for both of the unpromoted materials and tetragonal forms for all of the materials with the promoter. We have looked at the cubic structure of ceria and the structure of the La2O3, and with X-ray diffraction we don't see any peaks responsible for those structures. Previous work done by Naraha and Rosasco's group have shown that if you have less than 25 weight percent ceria, you have a higher fraction of ceria on the surface than on zirconia, indicating that you have less formation of a solid solution with that lower loading of ceria and lanthanum. So what we expect is that we don't have any change in structure. The zirconia is able to maintain its tetragonal form, but that we probably have some islands of ceria or some islands of lanthanum on the surface. And we've actually done SEM studies and used EDAX to look at the surface, and we see areas where we see just ceria or just lanthana as opposed to ceria zirconia mix. If we look at the comparison of the platinum loading, and this compares the blue is the 0.5 weight percent as opposed to the 1.5 weight percent, we see an initial increase in the rate of deactivation initially on the catalyst with the lower loading. And this was somewhat of a surprise to us because we thought with the catalyst with the lower loading we have a higher interfacial area, so we should have less carbon deposition, less deactivation. What we think is happening here is that we are having sintering of the metal occurring because after about 5 hours on stream, the rate of deactivation for both materials are very similar to each other. And so after that initial rate of sintering is occurring, you have similar materials and similar rates of deactivation. If we look at now the effect of the ceria and lanthana on dry reforming performance, we see that the individually promoted materials, the materials with the lanthana by itself and the ceria by itself, have very high activity and minor deactivation over the course of a 15-hour experiment with a 1-to-1 ratio of methane to CO2 at high space velocity. When you compare that to the platinum zirconia, you can see now here, this is the one with rapid deactivation, so there's a significant difference in those materials, even at a 1-to-1 methane to CO2 ratio. If you look at where the 1.5 weight percent platinum catalyst would have been, again, that ends up being somewhere in this range with a final activity of around 30%. And so even with the lower loading of material, even with 1/3 the amount of metal, the promoted materials perform much better than the platinum zirconia catalyst with 1.5 weight percent. What we found is that the addition of both ceria and lanthana did not result in improved performance. And so we see not only a decrease in the initial activity compared with the other catalysts, but no improved performance on this material. It does, however, perform better, slightly better in long-term studies than CO2 pulses. You see that there's a decrease in the formation of CO during this step, which could be indicative of the fact that the addition of ceria or the presence of ceria with lanthana results in a decrease in that activity of the carbonates on the surface. And then again, we see reducibility after the production of, or after the pulse of CO2. Temperature programmed oxidation experiments that have been done. Previous work has shown that on the ceria promoted material, you have similar amounts of carbon or slightly more carbon than on the zirconia by itself, but that the addition of the promoter moves the majority of that carbon to lower temperatures. And XPS studies have shown that it's the same type of carbon, but just the location of the carbon is different. And on the ceria promoted catalyst, you virtually have a carbon-free metal support interface where you may have carbon deposited in other places away from the metal. If you look at the TPO for carbon deposits on lanthana ceria promoted catalyst, and this is the TPO here, it's been expanded so you can see the regions. You see that you have features for both the individually promoted catalysts. You have the low temperature peak and high temperature peak. And the amount of carbon deposition for this material lies between that of the ceria promoted and lanthana promoted catalyst. The most interesting results that we saw were the temperature program reduction of the material. Down here is the reduction shown for platinum on zirconia. You can see that the metal reduces at approximately 200 degrees. If you look at platinum on ceria by itself, that reduction happens at about 120 degrees Celsius. And when we have ceria present on the catalyst, we see a slight shift in temperature for that platinum reduction. On the lanthana or zirconia material, we see a shift to higher temperatures for the reduction of platinum. And we also see the reduction of the formation of this peak here, which is most likely due to the reduction of the lanthana material. If you look at the lanthana ceria promoted catalyst here, we have now a very sharp peak, which is at higher temperatures, about 270 degrees, and the amount of hydrogen that's consumed here is approximately equal to the amount of hydrogen for this peak and the amount of hydrogen for that peak. And so now what we're seeing is that we have a reduction occurring for the platinum and the lanthana, and possible either electronic modification of the platinum or changes in the lanthana due to the presence of the ceria. If we look at now what happens when we have oxygen in the system, we can see that really there is no distinguishable difference in the activity for all of the promoted materials. However, they still perform better than the unpromoted platinum zirconia catalyst. The hydrogen to CO ratio was high for these materials and constant throughout the experiment. If we change the amount of oxygen and change the methane to the CO2 and O2 ratio, we again see very little difference in the promoted materials decrease here in your CO2 conversion, and in some cases, if you let it go for a long time, you can actually see CO2 production. And what's happening is you're basically having methane plus oxygen going to CO2 in water. So as your concentration of oxygen gets really high, you're basically forming your combustion products. And we do have a significant amount of water collected during the experiment. Just to show, at the last slide, is to show that the ability to tune the hydrogen to CO ratio on the platinum series zirconia that we can take and we can run the dry reforming reaction for about an hour and a half. We can switch now and add oxygen at a ratio of methane to O2 of 4 to 1. And we see that we really have no significant change in our activity, and maybe 1% or 2% different from when we ran just purely in the presence of oxygen. And our hydrogen to CO ratio, again, we can change it from roughly 0.7 or 0.8 up to 1.4. And again, what we're looking at now is trying to see we do these same things in the presence of steam to try and see if we can really get hydrogen to CO ratios anywhere within that range. So in conclusion, we showed that perovskites and strontium cobalts are not suitable supports for the dry reforming reaction, although this material with nickel in it has been shown to be very active for these reactions. Decreasing the amount of platinum loading on zirconia increased the initial rate of deactivation, which we believe is due to sintering, but then after that, the rate of deactivation was very similar to the higher level material. Promotion of lanthanum ceria increased the activity and stability of the material compared to the platinum zirconia, even with the lower loading of metal. When you add lanthanum ceria together, even though you have a high surface area and you have comparable dispersion, you have increased reducibility. We don't see increased activity, and that could be due to possible electronic modification, which we're trying to look at using Zane's techniques, using IR spectroscopy and also XPS, and a decrease in reactivity of carbonates, which we're also looking at with IR studies. In the presence of oxygen, all the promoter catalysts exhibit high activity and stability, whereas deactivation is still observed on the platinum zirconia materials. And on the platinum series zirconia, we see no significant change by switching the feeds. And previous studies have shown, unpublished studies have shown that you can see similar effects with water, so that this is a possible candidate for the miniature program. And with that, I'd like to acknowledge the supplier of the materials, my grad students, and funding for this project. Thank you very much.
So we have time for maybe one short question before we'll start into our break. Bob?
Methane conversion seems low compared to steam reforming. Can you comment on that?
We're using, in these cases, we use very small amounts of catalyst in order to be able to have low methane conversion, so we're not anywhere near equilibrium conversion. So the amount of material that we're using here is about 15 milligrams of catalyst at very high space velocities. So these can't be compared to commercial conversions.
If we have any additional questions for the speaker, I recommend taking those at the break time. We'll reconvene at 10:45 for the storage award honoring Bert Davis, and we'll see you in a few minutes here.
Transient kinetic